In this video I'm going to be working through a series of integration questions that I gave to the class last week. It's a mixture of different ways of integrating, different methods. This first question was quite difficult. It's actually probably more like a 10-mark question because it involves two processes. So we've got this curve given by a complicated equation with trigonometric functions, and we've got also the normal to the curve there. Find the exact area of the shaded region enclosed by the curve, the normal to the curve, and the y-axis. So this is going to have to take two processes. We've got the integration to get this area above the axis, but to find this area below the axis we are going to have to differentiate to find the gradient at this point, the tangent, and then find the gradient of the normal, find the equation of that line, and therefore find where it crosses the axis, and at that point we'll be able to work out the area of this triangle below. So the first thing I'll deal with above the axis, and that's just going to be the integral from 0 to quarter pi, which I'll just put as pi over 4, of this function that we were given at the start. With respect to x. Now this function can be integrated by inspection just by looking at, we've got this link between the sine 2x here and another number, and cos 2x is some multiple of the derivative of sine 2x, so this will work by inspection. However, if you didn't spot that, then there is a method using substitution as well, which I can go through at the end of this. So first of all I'll just do the by inspection method. So you might just spot this straight away, but if you're not completely fluent with it, you would look at what's on the denominator and you would try see what happens if you differentiate ln of 3 minus sine 2x. And if I do that, I get something over, because it's ln, so that goes straight onto the denominator, which is why I've chosen it, sine 2x, not 2 sine x. And on the numerator, let's see what happens. I'm differentiating minus sine 2x, so sine becomes cos, and the 2x means that I'm doing 2 cos 2x, but that minus sign from that is still there. So I end up with minus 2 cos 2x over 3 minus sine 2x, and if I compare that with what I want over here, I do want this same thing, but I want it to be, instead of a multiple of minus 2, I want it to be 4, which means that I need to multiply this whole thing by minus 2. If I multiplied this answer by minus 2, I'd end up with what I want, and therefore I need to multiply this bit by minus 2. So the integral of that is the integral, like I said, minus 2 and whatever I put here, minus 2 ln modulus of 3 minus sine 2x, integrated from 0 to pi over 4. You want to make sure you're using this notation properly, with the modulus signs and with the square brackets once we've integrated. Now I'm going to put these limits into the function. So that equals, with pi over 4, sine of 2 pi over 4 is 1. Think of that as 45 degrees, and 2 45 degrees are 90 degrees, so sine 90 is 1. So I've got minus 2 ln 3 minus 1 is 2. And then I need to substitute in the 0 to that. Sine of 0 is 0, so I've just got minus, in this bracket, minus 2 ln 3 minus 0, so it's minus 2 ln 3. So that gives me minus 2 ln 2 plus 2 ln 3, and that is the area in here above the axis. So I've then got to deal with the area below axis, and for this I need to do a differentiation of this function 4 cos 2x over 3 minus sine 2x. I'll be using the formula for the quotient rule from the formula book, which tells me that if I want to differentiate f of x over g of x, my answer will be g of x f dash x minus f of x g dash x all over g dash x, no, just g of x, sorry, just g of x all squared. So essentially what I want to do is, so I'm finding dy by dx. First thing I'll do is write out that denominator squared, and that's my g of x squared. Also, the first thing that appears on the top line is that g of x function as well. So I've got 3 minus sine 2x times by the derivative of 4 cos 2x, so doing chain rule with that. Cos becomes minus sine. I need to bring the 2 in front, so 2 times 4 is 8 now. Cos becomes minus sine, so I'll put that minus sign in front, and the 2x remains a 2x. And then I need to subtract f of x, which is 4 cos 2x, minus the derivative of what is in the denominator, so differentiate the 3 is 0, differentiate sine 2x and it will become 2 cos 2x, but we've got a minus in the bracket in front of it, so it's minus 2 cos 2x. All squeezed in there, minus 2 cos 2x. So multiplying that out, that gives me, you know what, I'm actually just going to drop in the value. I want to know at this point here, this is where I want to know the gradient of the normal. So I will find the gradient of the tangent first. So at quarter pi 0, dy by dx equals, and if I just substitute that quarter pi into all of these, so it's always a 2x actually, so it's always just pi over 2 or 90 degrees into all of those, I end up with 2 from that bracket, minus 8 from the second bracket, minus cos 0, sorry, that's cos 90, or cos pi over 2, which is 0, so I get nothing out of that bit, all over this bit squared, which is the result of 2 squared. So that leads to a gradient of minus 16 over 4, which is minus 4. Just line that up again. So gradient of tangent equals minus 4. Therefore gradient of normal is the negative reciprocal of that. So that is 1/4. And I use my y minus y1 formula using this point here. So I've got it going through there. So my equation is y minus 0 equals gradient quarter x minus pi over 4. And remember, I'm trying to find out what the y-intercept is, so that leaves me with y equals quarter x minus pi over 16. So that's my y-intercept. I'm going to label it up here. I could, another way of doing this altogether now that I've got that line would be to integrate this line between 0 and quarter pi. That would give me the area of this bit underneath the line. I'm actually going to do it with the area of a triangle. So area of triangle, I've got half the base times the height, which is a half times by the base length of a quarter pi times by the height here of pi over 16, and all those denominators multiplied to 128. So that equals pi squared over 128. And that means my total area, so I'd better start a new line at the bottom, is going to be the area above the axis, this bit, and the area below the axis, that bit. So minus 2 and 2, plus 2 and 3, plus pi squared over 128. Combining those two luns, that is 2 ln to, well, let's work this out. If I write it out in the other order, 2 ln 3 minus 2 ln 2 plus pi squared over 128. And now to simplify these into a single logarithm, well, these first two bits into a single logarithm, I've got 2 in front of both, so I can factorize that out. 2 ln, and I've got 3 over 2, and then I add this expression in terms of pi. And that is how I would expect to see the answer. Of course, this could also be written as ln of 9 over 4, that would be fine, but this is the simplest way to present that answer. So 2 ln 3 over 2 plus pi squared over 128. I did say I will do the substitution version of this integration at the end. This is definitely the easiest and best way to do it, but I will look at substitution because some people went straight for that when they were working through it themselves. So if I'm going to do this by substitution, I've got 0 to pi over 4, 4 cos 2x, 3 minus sine 2x dx. Now the only one I've used to check that it works, there will be other things that do work as well, but if I make u equals sine 2x, then du by dx, which is obviously the first step of a substitution, differentiate sine 2x and I get 2 cos 2x. That would be something in terms of u there. So when I do this substitution, I need to do my limits as well, of course. So my limits in terms of x are 0 and pi over 4. That means that my limits in terms of u, I've got sine of pi over 2, so sine 90 is 1, and then I've got sine 0, which is 0. So substituting each of those things, this bit, whole thing, is equal to, let's replace, I'm not going to use a square bracket, that's confusing. So my integral is now from 0 to 1. 4 cos 2x I'm just going to write out because it's going to cancel in a minute. What I didn't do with this, du by dx is 2 cos 2x, and therefore dx is 1 over 2 cos 2x du, and I need to get a replacement for dx. So substituting in, I'm just going to move all of that up a bit. Each part of this, I can see that this cos 2x in the denominator is going to cancel with a cos 2x there. So I get 4 cos 2x over 3 minus u, which I'll replace that, times by 1 over 2 cos 2x du. And so here the cos 2x is cancelled, 2 cancels with the 4, leaving with 2 on the numerator. So this whole integral is going to be from 0 to 1, 2, everything else is cancelled, over 3 minus u, with respect to u. So when I integrate that, I get it's just 2 lots of ln 3 minus u, the denominator, from 0 to 1, which also gives me 2 ln 3 minus 1 is 2, minus 2 ln 3 minus 0 is 3. And that's exactly what I got before up here for my integral. So I've ended up with the same, apart from I've gone from plus to minus. How has that happened? It was a minus u here. That should have been a minus in front of all of it, because it's minus u in the denominator, and therefore there should be a minus in there. And therefore that's a minus 2 ln 2 minus 2 ln 3, ending up with exactly as I had before. So apart from that slip because I was going too fast, this is actually an easier thing to integrate, but it takes a while to set up that substitution. So, like I said before, best method is going to be this first one, just integrating by inspection. And that's a lot of information on the screen, but there is my final answer, 2 ln 3 plus pi squared over 128. Okay, next question. Okay, so in question 3, I think there's a bit of a misprint. This should say that given that k is a member of the set of real numbers, k is a real number, otherwise it doesn't really make sense. But anyway, we can still do the question. Show that integral of k to 3k of 2 over 3x minus k with respect to x is independent of k. And this means that I'm hoping for my result not to have any k in it. So by the time I get to the end of the whole thing, my result should not include k. That's what I'm hoping for, although you might not know that when looking at the question. If you don't know that, we will just go ahead and integrate, because that's all you can do with this question. So I'll do that now. Go ahead and integrate from k to 3k, 2 over 3x minus k with respect to x. Now I can see this as a ln situation because I've got a linear denominator, so it's going to involve ln of 3x minus k, and if I think about differentiating that, again, if you're really fluent with this, you'll just do it immediately without needing to go through this process, but I'm just showing the process of trying something out. If I differentiate y equals ln 3x minus k, I will end up with obviously 3x minus k on the denominator, that's why I've chosen it. And on the numerator is the differential of this, so that is just 3, and the minus k disappears. So that's what I'd get, that's what I need, but instead of having a 3 in the numerator, I have a 2 in the numerator. So that is just a 2 and divided by 3. Divide by that 3 and times by that 2 instead to get what I need. And of course that is from k up to 3k. Substituting each of those in, that gives me 2/3 ln, I've got 3 times 3k, that's 9k minus k. Minus the other bracket with k in it, 2/3 ln, if k is x, that gives me 3x, sorry, 3k x is replaced by k minus k, which is 2/3 ln 8k minus 2/3 of ln 2k. I can factorise out the 2/3 in front of that, so that is 2/3 ln 8k over 2k. The k's do cancel each other out, so I end up with 2/3 ln 4, which is independent of k. As in, it doesn't matter what value of k I put into this, the result will be the same, because k is not involved in the answer. When I get on to part B, given that k is a real number again, it should be like the one above, show that integral from k to 2k of 2 over 2x minus k all squared dx is inversely proportional to k. I am hoping for, let's just think about what this means, the integral, which I'll just call I, should be proportional to 1 over k, and therefore should be equal to some multiple, I'll just call it m, times by 1 over k. That's what I'm hoping for if I'm going to show that it's inversely proportional to k. But again, to show that question, we're actually going to have to do it to get that result. So this time I've got 2 over 2x minus k all squared with respect to x. And of course, because I now have a squared on the denominator, I can use up to the power of minus 2 and use chain rule with that, or reverse chain rule. So k to 2k of 2 lots of 2x minus k to the power of minus 2 with respect to x. So thinking about integrating that, I would have started with something with that to the minus 1. When I differentiate that, I'm going to get something involving what I want here. I would have, bringing that minus 1 to the front, the thing in the bracket, reduce the power, and multiply by the differential of what's in the bracket, so 2, so that's all chain rule. And that gives me minus 2x minus k to the minus 2, which is what I want apart from negative. Therefore I must have started with that with a minus sign in front. So my integral is minus 2x minus k to the minus 1 from k to 2k. Substituting into that, that gives me minus 1 over, because I'm going to flip this is over that denominator, 2 times 2k is 4k, minus k, minus, and again, that bracket there, minus 1 over, when x is k, 2k minus k is just k. So that equals minus 1 over 3k plus 1 over k. I can rewrite that as a fraction with the same denominator, so that is plus 3 over 3k minus 1 over 3k, which is 2 over 3k, which is 2/3 of 1 over k, and remember I'm trying to get it back so that I've got this integral is some multiple of 1 over k, and I've shown that there. So as a final statement, it does say show that, so I'm just going to write a final statement. So the integral equals 2/3 1 over k. Therefore integral is proportional to 1 over k. And that's shown what needs to be shown in that one. Okay, next one, question 4. Using integration by parts to find the integral of x sine 3x dx. So hopefully this will be quicker. It's only a 3-mark question. So in this I need to define my parts. I've got u equals, I'm going to choose u equal to x, of course we always do that if we can, and therefore dv by dx is the other thing, sine 3x. Differentiate that, du by dx equals 1, and integrate that, integrate sine 3x, it needs to come from cos 3x, but of course when I differentiate cos, the sign changes, so I'm thinking of cos 3x. I've also got the 3 inside, so that's going to be a third, and I just need to think if I differentiated a third cos 3x, I would end up with minus a third, minus sine 3x, so to deal with that I need to put a minus sign in front of that. So I get my integral. Remember, this is by parts uses the rule that integral of u dv by dx with respect to x is equal to u times v minus the integral of v du by dx with respect to x. So my integral here is equal to u times v across there, sorry, minus 1/3 x cos 3x minus the integral of v times du by dx, which is 1, so it's just minus the integral of that, minus a third cos 3x with respect to x. So now working from this backwards again, I've got most of this now, I just need to integrate that bit. This bit, again, dealing with that 3 in it is going to make it 1/9, so again, thinking about where it's come from, I'm going to think about sine 3x. I know that cos is going to go to sine. That third is going to be multiplied by another third, so it becomes 1/9. And because I'm going from minus cos, that will stay as a minus sign. When I integrate cos, the sign stays the same. Or when I differentiate sine, the sign stays the same. So same thing going on there. So I end up with minus 1/3 of x cos 3x minus 1/9 of sine 3x plus c. And just to deal with those double minus signs, final answer will be minus 1/3 of x cos 3x plus 1/9 sine 3x plus c. Final answer for that one. And that's it for this video. Second video I'll be doing second part, I'll be doing questions 5, 6 and 7.